And we're back. Welcome back and happy Tuesday. Today we will continue on in our discussion of the application layer. Specifically, we're going to be looking at HTTP, the protocol that underlies the World Wide Web. Before we begin, homework number 1 is due this Friday, the 5th of February at 10 a.m. Please make sure you note this time. I gave you till the next morning because the homework was late in being released last week. So that is Friday, the 5th of February, 2021. This Friday at 10 a.m. That's 10 a.m. All right. So when we last left off, we looked at non-persistent HTTP. And we went over the interactions between the client and the server. In doing so, it begins with a URL, some domain name like someschool.edu, some folder name, ending in some HTML file. And so the first thing that happens is the client initiates a connection. And you notice this first round trip, the outbound message from the client establishes with the server whether or not it can participate or has resources to participate in the upcoming interaction. And so the server at that machine waits for an incoming connection. It gets that connection request from the client. It accepts that connection, and then it sends back a response on the return trip, and that's the edge going from right to left. And so in returning that message, accept of the connection request, the server checks its resources to make sure it has all of the things that it needs, both computation ability as well as buffer space and variables and other things that it needs to engage in the interaction with the client. And so the server does some work after it gets that message and returns back either an accept or a reject response. So the client then gets this and says, hey, all right, great. Now that I know the server in step 2 is able to participate, I send my message. So this client sends this HTTP request. It's requesting some file system object, some resource from the server. So it sends that message to the server receives it, it chops it up or parses it, and the work that the server does in turn will be to retrieve that resource from its local file system and send it back as a response across the wire. So this response goes back to the client, and after doing its part in sending back the response, the server, HTTP server, closes its connection. It's TCP, Transition Control Protocol connection. So then the client receives the response, and it contains the HTML file, and it displays that HTML file and realizes when it parses or chops it up that there are 10 JPEGs, for example. It could be images or what have you. And so this set of steps, the connection request and then the fetch request and the response with the content, that's repeated, the steps 1 through 5 for each of the 10 many JPEG objects. So that's where we left off last time. So let's take a look at non-persistent HTTP response time. And let's introduce a little bit more definition so we all know what we're talking about and use well-accepted terms in the literature. Let's define RTT, or round-trip time, to be the time it takes for a negligibly small packet to travel from the client, and here's the client, this column in our protocol diagram. Here's the server on the right-hand column. And the RTT is the time it takes for a packet to travel from the client to the server and back again, hence the name round-trip time. And so the HTTP response time is that time for one RTT to initiate the connection and one RTT for the request to get the first few bytes of that resource or response it gets from the server. So let's take a look at the protocol diagram and ground all of this in what we see in the protocol diagram. So we start out and time goes down in the downward direction. The client initiates the TCP connection, and in one round trip, it gets back the accept request. Okay, the server is ready to do its thing. And that's one RTT. So then on the next round trip, we get the request, and then we get the first few bits of the response. That's another round trip. And then we add to that the amount of time it takes to transmit the rest of that file, which it comprises the response from the server going back to the client. And so the total response time is the sum of all of these things. It's the time it takes to initiate the connection. That's one round trip time. The time it takes for the first few bits to arrive after making the request. That's another round trip time, plus the amount of time it takes to transmit the file. That's this last part. And so for a non-persistent HTTP interaction between the client and the server, it requires 2 round trip times plus the file transmission time for that connection. So if you have 10 objects, each gets its own unique TCP connection, you're going to pay the cost of this 2 RTT plus file transmission for each of those objects. So the difference between non-persistent HTTP and HTTP we alluded to before, but when we look at the implication as it pertains to the time it takes for an interaction between the client and the server, they're a little bit different. So non-persistent requires 2 round-trip times per object. That's the connection request, and that's the GET request and the subsequent first few bits of the response. And there's overhead in the operating system for each TCP connection. Part of that connection request includes the allocation of resources needed to manage that connection, and we'll talk about that in detail when we get to the transport layer. But nonetheless, it requires more overhead for non-persistent HTTP, and browsers often try to speed things up by opening a lot of TCP connections in parallel so that you get each of those 10 reference objects at the same time rather than doing it one after the other sequentially. Persistent HTTP is one where the server leaves the connection open after sending back the response. And so in doing so, any subsequent interaction between the client and the server, like the GET request for some resource or object from the server, uses the same connection. And so you have as little as 1 round trip time for all of the reference objects, because that cost of round trip time for establishing connection, you pay that once up front, and you just pay the cost of just the GET and the file transfer for each of those subsequent objects that are transferred. And so this is what the HTTP request message looks like. This is what goes from the client to the server. And there are 2 types of messages. There's the HTTP request, that goes from the client to the server, and there's the response, which is what's returned back to the client from the server. And this is very purposefully simple. It's ASCII. Makes it easy to debug, easy to deal with. And so the HTTP request message is depicted as follows, and we have 3 sections to it in the anatomy, as it were, of an HTTP message, request message. We have what's called the request line. That's this first line, and that request line is an encoding of what the client wants the server to do. And we also have what are called the header lines. That's meta information that's very useful to the interaction between the client and the server. And then we also have the end part, which is just a carriage return line feed, \r\n. And so this request line in particular can have a bunch of operation codes. This is an op code, and that op code tells the server how it should behave, what it is the client is asking or requesting the server do on its behalf. And so this request line can be a get, post, or head command, and here it's a get. And what get means is that it wants the server to fetch some file from its local file system. So all HTTP really is just a file transfer system, a remote file transfer system. The file system resource or file system object is identified by this field. Here it says index.html, and it's relative to a root or top of a file system. Now, of course, that could have a folder hierarchy as well as a file name. But all it's doing is saying perform this opcode on that resource. Now, next is some bookkeeping information about which version of HTTP the client supports. And so this says HTTP version 1.1 because they need to come to an understanding of what the expected behaviors are on both endpoints or both parties in this interaction. And you notice here each line is ended with a character return line feed character, \R, \M. Now these header lines, these aren't required, but they're very important to the interaction. So these header lines are purposed with all sorts of useful information. For example, what the language is so that's supported by the client. And if you've ever used some websites that are multilingual, if you connect to them from an English-speaking locale, they return content for the website that's in English, or French-speaking locale returns content for the website that is in French. Well, that's due to this accept language header line entry. And so these header lines are name value pairs. And here we have the name, and colon separates the name from the value, and the value is that string that follows the colon. And so here it says the accept language in which you accept the connection is US English. Also is another one, the host, where the content is owned, is www.net.cs.umass.edu. Likewise, keep alive, how long to keep the connection open, 115 seconds, and whether the connection is persistent or not. Keep alive means keeps it alive. It's a persistent connection. And so all of this controls the behavior, but the header lines are informational, and it's useful things that the server can use. But the actual behavior, the ask that the client has on behalf of the server, is this request line in HTTP. All right. So here's the general schematic of what, or schema of what the HTTP request message looks like. You have some method drawn from a set of opcodes separated by space for all the different fields in the request line. You have a URL, Uniform Resource Locator. You have space, the version number for the version of the protocol, and character return line feed. So then you have the header field name, space, and then the values, so name value pairs. And then you have a character return line feed, and then optionally an entity body, which was built there in the protocol specification if you're going to do it to a post method, which posts aren't usually supported very much these days. It's a security risk. And so this post message allows a web page to accept data from, or the server to accept data from the client. And this information is uploaded into the server. Hence, that's a pretty big security risk. Typically what's used when you're entering in forms or data from the web browser of the client, and you want that to go or get uploaded to the server, is something called the URL get method. And what that does, it uses the get method, and the input is loaded in the URL. And so how they do this, for example, you'll notice it says somesite.com/animal search, and then it says monkeys banana. And so this animal search gets a list of parameters, monkeys, and these parameter, and banana. These parameters are delimited or separated by this ampersand. And in fact, if you ever go to YouTube, you go to youtube.com and it says V equals, and it has a hash code following. V equals means video equals. Uses the URL get method. So there are different methods or opcodes for the request field in the opcode field in the request line. And the difference between HTTP 1 and HTTP 1.1. The big difference has to do with the put, where put can upload a file into the server. Also the delete. And outside of that, put and the delete, HTTP 1.1 supports everything that's also in HTTP 1.0. So when they went from 1.0 to 1.1, they added this ability to upload files as well as to delete. Okay. Now you, as the person that deploys the web browser, or web server rather, you do not have to support certain methods. You can say, I'm not going to do it. All right. So this is the response back to the browser or the client from the web server. It's stylized. You have your status line, which tells the client what the server's result was of that operation. It tells the client also what version of HTTP was supported by the server. And of course, each one of these lines, the status line, is the response back. We also have header lines that describe meta information associated with the status from the server. So in this particular case, it says the server supports HTTP 1.1, and there's a status code that tells what happens. The server is okay, it had no problems. And then there's a text version or textual description of that status code. It was okay. Carriage return line feed, /r/n, to delimit this particular status line from the rest of the HTTP response message. And so we also have, again, our header lines. These are name value pairs. And for example, what type of server was on the server side of this connection? Is Apache version 2.0.52 running on CentOS operating system? Okay, so there's lots and lots of information that is trafficked back and forth, as well as the request and the status. And then after the header lines, we have a carriage return line feed, and that carriage return line feed does not follow any or text. It's just there to say, okay, well, the status portions and info portions of the response are done, and what follows that carriage return line feed is going to be the actual data itself. So that's where the contents of the file would exist if the command were to get a particular JPEG file, image file, or HTML file. And so these are what the status codes mean. 200 means okay, everything was fine. Status code 301, move permanently, bad request, file not found. You'll see error 404. You bring up a browser and you try some weird website. It'll say error 404. Some websites will write the text. Some will display a special error page. Some will display an image. It really depends on how you've deployed or how the webmaster for that particular website you're connecting to has deployed and configured their Apache. Now, I say Apache specifically because Apache is the predominant, the open source web server. Apache is the predominant web server being used in deployment today. So let's try out the HTTP client. And we're going to try this out, and this is in the book, using telnet, which is just a tool for connecting to various applications at various ports. And we're going to type in the GET request, and we're going to show what happens and show the response back, which is the HTTP response as text. Let's look at the command that we have. So we're going to try telnet, Gaia CSU Mass EDU, port 80. So we're connected to now get Kurosa Ross interactive index.php HTTP version 1.1, and then host is gaia.cs.umass.edu, carriage return. And what we get back is the PHP file for that particular website for Gaia CSU Mass EDU. Okay, so let's go back to PowerPoint, and your browser does the same thing. Telnet opens up a TCP connection to port 80, which is the default HTTP server port. That's where your Apache web server is running. And anything typed will be sent to that process, your web server process, listening on port 80 on that machine, identified by gaia.cs.umass.edu. So now we typed in the request with a single header line for the host specification, hit return twice, that's the carriage return line feed for the end of the line, and the carriage return line feed to end the client request. And then we saw that response message that came back across the wire to our telnet session from the server. All right, so HTTP is stateless, and there are some applications, such as electronic commerce and shopping, where you want to maintain some kind of state information, context between the client and the server. And so there's a header line that implements this persistence, and this header line is something called a cookie header line. And this cookie header line is specified by the client when it connects to the server, and this cookie information is stored locally on your client machine. Your client machine, your client furnishes this cookie information to the server, and the server then looks up that particular cookie information to identify that particular client. And so the cookie is initiated when the client connects. On the response, the server includes a set cookie spec in the header line, and in response, the client creates that cookie information, and on subsequent requests, that client furnishes that cookie information. So the cookie file is both kept on the client, but also on the server. The server maintains an entry in a database containing all that information, contextual information associated with that client. So let's take a look at it. Suppose you are on your machine and you initiate a request to, let's say, Amazon. And Amazon, when you do your search, it creates an ID for the user and an entry in the backend database. When it returns back a response, one of the header line entries is set cookie. So the set cookie for Amazon.com has a value, the cookie value, of 1678. So when your client gets this, in addition to rendering or drawing the HTML file that you see as the Amazon web page on your browser, it also creates a cookie entry locally on its file system. So you search and search and search, and it identifies you by this cookie ID, 1678, specifically identifies your browser as your identity. So now, subsequently, you initiate a new request to get content from the Amazon web server, and your client says, oh, I'm going to Amazon.com. There's a piece of cookie information for Amazon.com. Let me go ahead, read it. I see it's 1678, so I'm going to furnish that and include it as the cookie header line entry, 1678. So then you come along and you send a request, GET request, to Amazon server, and it says, oh, there's a GET request. Oh, wait a minute. That's user number 1678. I've seen that person before. So let me pull up the database record information for that user, and then I give you a response that seems like it's customized, which it is, to you. And so 1 week later, you come back, and guess what? You make another GET request. It says, oh, welcome back, 1678. How did you like that item that you bought? And you're like, oh, how did you know that? Well, it's because of the cookie information. All right. So this is how state is implemented. So we're here in Google Chrome, and we've gone to Amazon.com. So now I'm going to type in, maybe I like the Xbox Series X, and I'm going to search for that. And I browse around, and I say, oh, Xbox Series X. They're hard to find these days. Currently unavailable. Oh, that stinks. All right. Well, let's look at the Xbox One S 1 terabyte bundle. Okay. $545. Okay. So now let me go back to google.com, and then I will go back to amazon.com. Search for Amazon. I click on Amazon. I revisit Amazon. And then when I go down below, I see all of a sudden, hey, wait a minute. How did it know that I viewed these things and it's recommending something for me? The reason why it knew is because of that cookie information. And if I were to clear the cookies on my browser, it would treat me as if I were brand new all over again. Okay, so that's cookies in action. Let's go back. So what can cookies be used for? Cookies can be used for authorization, shopping carts, recommendations, all sorts of things. And cookies allow sites to learn a lot about you. if you want your privacy, you need to clear your cookies. And there are some browsers that allow you to go into so-called private mode, meaning that when you browse and you're done and you exit the browser, it clears all those cookies for you. So that when you go to subsequent sites, you visit a website and then search for something and then visit some other website, and all of a sudden the other website knows something about what you've been looking for. Well, that's because of cookies. So this keeping of end state, while HTTP does not itself involve state, it's a stateless protocol, using cookies, the endpoints themselves maintain state at the sender and receiver over multiple transactions. And these cookies carry state information. You can identify or associate a particular set of activity with a particular user. All right. So let's take a look at web caches. Now, this is a web cache that you might see on a network level, a so-called proxy server, and we see web caches in your browser. This is not the same thing. So the web cache that you see on your browser is storage underneath your browser on your local file system. So your browser cache consists of storage, and whenever you reach out over the web to a server, the content that's pulled down by the server that you display is loaded into the cache. And so when you make a subsequent request to that server, rather than fetching all of that big information like JPEGs and things like that all over again and paying that cost, it's a lot faster to just load it from the hard drive instead of fetching it each time from the server. Sometimes it's called an origin server because it's the origin of the content. So when you click your browser and you hold down the shift key and hit reload, well, that holding down the shift and doing reload says ignore what's in the cache, fetch it from the origin server. So in similar fashion, this cache here on the browser, it's intended to save the time by loading it locally because local access is faster. Now we can do this at a network level. At a network level, it's called a proxy server or a web cache. And let's imagine you're on a network like DSU's Campus Enterprise Network, and you have a client machine. Instead of connecting directly to the origin server to get your content, you connect to the so-called proxy server. And so you as the client initiate an HTTP GET request, and it goes to the proxy server, and the proxy server checks its local storage and sees it does not have a copy. So it goes out onto the internet, forwards a request to the origin server to get that content. It receives back a response from the origin server. It then stores a copy of that content in its local storage, in its cache, and then returns an HTTP response to the requesting client. So now, let's imagine that content was popular content. Another client on the same network comes along, and it wants to request the same content. And all of the requests go to the proxy server before they go out on the network. So that second client comes along, it initiates HTTP requests for the same content. This time, the proxy server has a copy of it in its local hard drive. So it looks in its hard drive and says, aha, I have a copy, so let me take that copy, pull it into memory, and send it back across the wire in an HTTP response rather than reaching across the internet to the origin server to fetch a new copy of that content. Okay, so what we see here is that for subsequent accesses, it's a lot faster because it's local. And so a cache acts both as a client and a server. You could say it's a peer if you wanted to, but it acts both as a client and a server. It's a server with respect to the original client request, and it's acting as a client in terms of its relationship with the origin server. Now, these caches, web caches, are typically installed by the folks that manage the network, like the IT department at DSU, by your service provider, so forth. So why do you do web caching at all? Well, because that reduces the response time, especially for frequently accessed content. And because these requests don't go across the internet to the origin server, it eases the load on your access link for your network. If you have a network that has a lot of web caches, you effectively serve the role as the poor man's content provider. Because if you cache enough content, you're providing content, for example, on behalf of Google, if enough people are searching for Google images and downloading them on your network, and they're being stored in caches all over your network. And so this is an example in the book. It's a caching example. And we have in this figure an enterprise network, institutional network, or enterprise network, like you'd have at DSU. And so we have a bunch of hosts connected, and we have our local area network is 1 gigabit per second, really fast. So then the access link for the gateway or router that gets data off of the institutional network onto the internet, that link has a bandwidth of 1.54 megabit per second. On the public internet side, that router, that gateway that connects traffic into the public internet, well, once you get data there, it just sends that information to other routers in the ISP, eventually making its way to the origin server sitting in a data center somewhere. And so let's assume that the average object size is 100 kilobit per second. So the client machines on the institutional network make requests, and you get your resource 100 kilobits, and these origin servers are sending them back down through the internet fabric in through the access link to the institutional network to the client. And so let's assume that we have objects of size 100 kilobit, and the average request rate from these browsers to the origin servers, and therefore the average rate at which content is going to get delivered, is 15 requests per second. So we have 15 requests per second. Each object is 100 kilobits. We multiply 15 by 100 kilobits, we get 1.50 megabit per second. So given this average data rate that we get going from the origin server back to the browsers running on the clients, given that that aggregate rate, the average times the object size, the average request rate times the object size, we multiply, given that it's 1.5 megabit per second, well, that's very close to the 1.54 megabit per second transmission rate or capacity for that access link. And so if we were to look at the utilization of that link, how close to being fully utilized, well, that would be 99%. 1.5 over 1.54 is 99%, roughly. And let's further assume that the round trip time from an institutional router to any origin server is going to be 2 seconds. So that's from here, that's on the internet side of the network. To have a round trip to an origin server and back, that's going to be 2 seconds. And that's usually the case because you have multiple hops, and that's not too far-fetched. You have multiple hops and a lot of links to go through and so forth. Let's assume that your local access network, well, since it's gigabit, the time it takes to send data back and forth, the delay, is going to be negligibly small, like microseconds. So if we were to look at the components involved in a total delay, well, what happens? We go across the local area network, that's microseconds. Then we go across the access link, that's in the unit of minutes because it's almost fully saturated. It's 99%. And we said that when we talked about traffic intensity, we said the delay gets much, much greater as you get more and more saturated. Your capacity is approached. And 99% is almost, you might as well call it full capacity. So we have the access link takes minutes, and then it takes 2 seconds for that last portion to get that traffic from the institution side router in your public internet to the origin server and back. So this is going to be our delay. It's going to be on the order of minutes, and that or minutes delay for the access link is going to dominate the delay that we're going to see end to end between the origin server and the clients on the institutional network. And this just goes back to what we talked about when we had our discussion on bottleneck links. It's the bottleneck link that determines the end-to-end throughput. So now, this saturation, that 99%, is a huge problem. So what could we do? Well, you might say, gosh, well, let's just buy more bandwidth. And that's a solution. And it would actually work. Now, if we bought, say, 100 times more bandwidth instead of 1.54 megabit per second, yeah, that's kind of small, you might argue. Let's say we bought 100 times, 154 megabit per second for our access link. So, of course, we could absolutely do that. Now, if we did, what happens? The utilization, instead of being 99%, it's 9.9%, because given the specification of the object size and the average rate, that's 15 requests per second times 100 kilobits per request, that's going to be 1.54 megabit per second. So it's going to be 9.9%, roughly 10% of the access link between the institutional network and the public internet is only going to be 9.9% utilized. So that's not very much. So it's going to be pretty fast. So if we were to redo our calculation about the total delay end to end, well, the internet delay, that hasn't changed. That's 2 seconds. The LAN delay locally on that gigabit network, that hasn't changed. That's in microseconds. And lastly, the one that has changed a lot is the access link delay. And that's going to be in the order of milliseconds, because we're not using too much bandwidth of the access link. Fractionally, it's relatively small. It's 9.9%. Now, of course, another thing, if we look at this, yes, that was a solution. It did work. But that was very expensive, because to get 100 times more bandwidth from your service provider, yeah, they could probably do it, technology limitations being a thing. But if they could, they're going to charge you for it. They don't do this for free. And so you're going to have that recurring cost, and maybe that's not the best thing you could do. So it's not cheap to increase your access link speed order of magnitude. That's a lot. It's asking a lot. So what can we do? An alternative, both in terms of the cost as well as the impact in the reduction of the access time, is to implement or install a web cache locally to the institutional network. Now, of course, if we did this, something very dramatic happens. So the cost of a web cache is very cheap. It's just a low-end machine. You deploy it, install some software, keep it running, and everything's good. So one of the questions we want to know, let's assume our LAN utilization is 15%, and where does that come from? Well, if we have 1.5 megabit per second and our LAN is 1 gigabit per second, that's 15%. Okay, so now let's look at the total delay based on access link utilization. So let's suppose that the hit rate for this cache, meaning the rate at which requests have their requests satisfied in the cache versus having to go to the origin server. Let's say 40% of the time you get such a quote-unquote hit. The request is satisfied at the cache. The remaining 60%, it's satisfied or needs to be satisfied at the origin server. So what do we do? So that means 40% of the time we have local access, and the remaining 60% of the time we reach out to the origin server to fetch that content. So in this particular case, the access link utilization is only going to be 60% of the requests that use the access link instead of the full 100%. And that's going to result in a dramatic savings in the access time. So the data rate to the browsers over the access link is going to be reduced. Before we had 1.5 megabit per second. That was the 100 kilobit times 15 requests per second. We multiply that by 0.6. That's just 0.9. And with that 0.9 megabits per second of effective bandwidth across the access link, that means that we're going to have a link utilization of 0.58 for a total of 58%. So we've almost dropped in half. We went from that 99% we increased the bandwidth hundredfold and got it down to 9.9. But here now, just by adding this web cache, we can get it down to 58%, cut it in half from the original 99. So let's take a look at the delay. So 60% of the time, the delay is going to be the full delay from the origin server, and then the remaining 40% of the time, that's what this 0.04 is doing, it's going to be the delay that you incur when you satisfy the request at the cache, meaning it's loaded from the cache and you don't have to reach out to the origin server. So we take our 0.6, multiply it by those 2 seconds we talked about before. We take 0.4, and that's going to be milliseconds to access locally from the cache, and that's roughly 1.2 seconds. Now, it's 1.2 seconds with this cheap solution, i.e. the web cache, versus if we bought increased bandwidth, it's a lot more expensive with the increased bandwidth because that's a recurring cost. So just by paying that cost once, maybe $1,000, $500 for a machine, you install the cache software, set it up, set it as a proxy, and that saves you a lot of time and money and that recurring cost. Now you notice here the access is 1.2 seconds. That 1.2 seconds, if we go back to our example with the increased link, well, with that increased link, yes, we have lower utilization, but we had access time of roughly 2 seconds. Well, guess what? With a cheaper solution, that's both cheaper cost-wise as well as, the ability to deploy it and make it work versus going to your service provider, you have decreased the speed as well as the cost. The access time is less by installing a cache with these numbers for hit rate versus buying 100 times the bandwidth. So this is the power of caching. It's this idea of locality that really, really pays off tremendously. And so let's talk about the mechanism that caching uses. And the mechanism is handled in HTTP in the header line section using a header line keyword or variable called if modified since. And what the goal is the client checks the date for an object that it contains locally against the date on an object on the server. And this date is what the value is associated with the if modified since header line entry. So our goal is don't send the object if the cache has an up-to-date cached version. And if you don't send the object, there's no object transmission delay. You're not encoding the bits of that object, and they can be quite big, like JPEGs and images. And this results in lower link utilization. So the cache, we said, acts like a client when it reaches out to the origin server. And so the cache is going to specify the date on the cached copy in its HTTP request that it makes to the origin server. And it says, if modified since this date. So then when the cache, which acts like a client to the origin server, reaches out and specifies if modified since, the server sees that, and its response contains information if no object if the cache copy is up to date. So if the cache copy is the most recent, i.e. the same date as what's on the origin server, it says, hey, it hasn't been modified. The server responds back and says, this object hasn't been modified. I don't need to send it to you. So the client then says, oh, okay, great. So I'm not going to go ahead and receive it from you, and you result in a savings in not having to transmit across the wire from the server back to the client. Now I say client not as the client machine, as the cache. The cache is acting like a client when it reaches out to the origin server. So you start out the cache acting as a client for the origin server. It issues an HTTP request message. Give me this JPEG file, for example. And it says, if modified since this date. So let's say the object is not modified before that date, All right. So then it responds back, "Oh, it has not been modified. We have the same version." So if the client makes a request, and let's say the copy of that object on the server has a later date, it's more recent, well, what does it do? It sends back a usual HTTP response message that says OK, the HTTP version OK message, as well as the data itself. And so in the first case, it says, hey, you're up to date. I'm not sending it, not modified. The second case, it says, oh, my copy is newer. Here it is. Here you go. It's a regular HTTP response message that includes as payload the bits of or data of the object that was requested. So essentially, this conditional get implements this notion of don't send it to me in the response unless what you have is newer. All right. So this concludes our module on the web and HTTP. And HTTP is particularly special because a lot of protocols out there are built on top of HTTP. Why? Because it's ubiquitous and it works. So we'll end there. And again, homework 1 is due this Friday at 10 a.m. Please make sure you note this extra time. It's not 11:59 seconds on Thursday. It's at 10 a.m. sharp on Friday, the 5th of February. So as usual, please stay healthy, stay safe, and I'll see you all on Thursday.